Hello there, and welcome to the Science for Sleep channel. Tonight, we drift into the profound story of natural disasters, those awe-inspiring yet devastating forces that have shaped our world for billions of years. From earthquakes that shake continents to tsunamis that travel across entire oceans, from volcanic eruptions that alter our skies to hurricanes that reshape coastlines. These violent wonders remind us of nature's immense power and our place within it. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light, as if gravity itself has softened its hold. Close your eyes and allow your thoughts to drift gently. Just before we begin, if this helps you find peaceful sleep, please consider liking and subscribing to our channel. One sleepy soul at a time. Now let's begin with the story of nature's most powerful events. The Great Flood of 1931 in China remains one of history's most devastating natural catastrophes, a tragedy so immense that it challenges our comprehension even today. Between 1 and 4 million people perished in just 5 months as the Yellow River unleashed its fury across the land, inundating an area larger than Greece itself. Entire cities vanished beneath the waters, and countless villages were erased from existence as if they had never been. The deluge affected a quarter of China's entire population at that time, transforming vibrant communities into underwater graveyards. Survivors faced unimaginable suffering, wandering through landscapes forever changed by the relentless water. This single catastrophe shaped the course of a nation and left scars that would echo through generations. Yet this flood, immense as it was, represents only one chapter in nature's vast and ancient story of destructive power. The Shanxi earthquake of 1556 in China struck without warning one devastating day and instantly claimed approximately 830,000 lives, making it the deadliest seismic event ever recorded in all of human history. In a single moment, cities collapsed into rubble, temples crumbled to dust, and countless families were torn apart by the violent shaking of the earth. The ground itself became a weapon of unimaginable destruction, tearing open in massive chasms while buildings folded like paper and entire populations vanished beneath the wreckage. Survivors emerged into a landscape transformed beyond recognition, where nothing remained as it had been moments before. The scale of this tragedy was so profound that it altered the demographic landscape of an entire region for centuries afterward. This earthquake reminds us that the solid earth beneath our feet harbors tremendous forces that can be released with terrifying suddenness and finality. The Yellow River's catastrophic overflow in 1887 became another chapter in nature's relentless story of destruction, as an estimated 900,000 to 2 million people perished in a single flood that devastated 11 major cities and hundreds of smaller villages. The river transformed from a life-giving force into a raging torrent that swept away everything in its path, leaving nothing but destruction and despair in its wake. Entire regions were submerged underwater for months, destroying crops, livestock, and infrastructure that generations had built. The survivors faced starvation, disease, and homelessness on a scale that the human mind struggles to comprehend even now. Trade routes were severed, economies collapsed, and populations were displaced across vast territories. This inundation shaped political and social upheaval that would define the century that followed. The sheer magnitude of this disaster stands as a sobering reminder of water's awesome and terrible power. The 1883 eruption of Krakatoa in Indonesia was so violently explosive that the sound of the blast traveled nearly 5,000 kilometers across the Indian Ocean to the island of Mauritius, making it the loudest noise ever recorded in human history. The explosion was so forceful that it destroyed much of the volcanic island itself, launching massive quantities of rock and ash high into the atmosphere. The eruption triggered tsunamis that rose to towering heights and crashed against distant coastlines, obliterating everything they touched. Ash clouds spread across the sky, dimming the sun and cooling the global climate for months afterward, affecting weather patterns worldwide. Approximately 36,000 people lost their lives in the disaster and its aftereffects, most perishing in the tsunamis rather than from the eruption itself. The sound traveled through the air for hours, a ghostly echo of nature's tremendous power. This event demonstrated how interconnected our planet truly is, with effects rippling across vast distances. The Bhola cyclone of 1970 struck East Pakistan with absolutely no mercy, killing between 250,000 and 500,000 people in a single devastating night that remains etched in the memory of survivors and descendants. A powerful storm surge pushed ocean water inland for miles, drowning entire populations as they slept in their homes and villages. The cyclone's winds were so strong that they flattened entire forests, turned buildings into splinters, and swept away everything that stood in their path. Families were separated in the chaos, many never to be reunited, and the humanitarian crisis that followed was almost as catastrophic as the storm itself. The economic devastation was complete, with the region set back by decades in its development and recovery. Survivors faced disease, starvation, and the profound psychological trauma of losing everything they held dear. This cyclone remains the deadliest tropical cyclone ever recorded in human history, a sobering reminder of nature's raw power. The Karinga cyclone of 1839 in India generated massive waves standing 40 meters tall that completely destroyed the harbor and devastated the surrounding region, with a death toll estimated at 300,000 souls lost in just a few terrifying hours. The cyclone's storm surge penetrated far inland, carrying salt water that destroyed agricultural lands and made them unusable for growing crops. Entire merchant ships were lifted from the water and deposited inland, an impossible sight that testified to the sheer force of the waves. The cyclone's winds shredded buildings to pieces and snapped ancient trees as if they were mere twigs before the overwhelming power. Communities that had existed for centuries were wiped from existence in a single night of terror and destruction. The survivors emerged into a landscape so altered that many could barely recognize the places where their homes once stood. This cyclone demonstrated that the sea itself could be weaponized by nature's fury to devastating effect. The Lake Nyos incident in Cameroon in 1986 represents a unique and horrifying type of natural disaster in which an invisible toxic cloud killed approximately 1,700 sleeping people without warning or visible signs of danger. Carbon dioxide gas accumulated deep within the lake from volcanic activity and was suddenly released in enormous quantities, rising as an invisible vapor that flowed downward into surrounding valleys. The heavier-than-air gas suffocated people as they slept in their beds, their families beside them equally powerless to resist the odorless, invisible killer. Livestock across the region died simultaneously, creating scenes of strange and disturbing silence. Scientists later realized that a similar eruption had occurred at another lake in Cameroon decades before, killing 37 people through the same mysterious mechanism. This disaster revealed that some natural hazards operate so silently and invisibly that humans have no natural warning system to alert them. The tragedy demonstrated that nature's dangers sometimes come without sound, light, or obvious warning signs. The 2004 Indian Ocean tsunami released energy equivalent to 23,000 Hiroshima atomic bombs, an almost incomprehensible amount of destructive power concentrated into massive waves that spread across the ocean at incredible speed. This tsunami killed approximately 230,000 people across 14 different countries, making it one of the deadliest natural disasters in recorded history. The earthquake that triggered it occurred on the ocean floor, displacing enormous volumes of water that compressed into waves traveling at 500 miles per hour toward distant shores. When these waves reached shallow coastal waters, they slowed and grew exponentially in height, sometimes reaching 100 feet or more at the shoreline. The destruction was so widespread that entire regions were set back decades in their development and recovery efforts. Communities that had existed peacefully for generations were obliterated in minutes as the waves crashed ashore. The tsunami served as a tragic reminder that the planet's interconnectedness means that distant events can have immediate and catastrophic local effects. The collapse of the Bongqiao Dam in 1975 during Typhoon Nina in China created a mud tsunami of water mixed with debris that killed approximately 230,000 people, demonstrating how human engineering failures can amplify natural disaster effects. The failed dam released an enormous wall of water and mud that swept through valleys at tremendous speed, destroying everything in its path with unstoppable force. Entire villages were buried under meters of mud and debris, and survivors faced impossible conditions searching for family members in the devastated landscape. The disaster revealed critical engineering flaws that had been ignored or overlooked during construction and maintenance of the infrastructure. The recovery process was slow and painful, with entire communities needing to be rebuilt from nothing. The incident sparked major reforms in dam safety standards worldwide and demonstrated the importance of proper maintenance and oversight. This tragedy showed that sometimes the combination of natural disaster and human oversight can produce consequences far worse than either would alone. The 1960 Chilean earthquake measured 9.5 on the moment magnitude scale, making it the largest earthquake ever recorded in human history, releasing unimaginable amounts of energy stored deep within the Earth's crust. The violent shaking lasted for several minutes that felt like an eternity to those experiencing it, toppling buildings and triggering massive landslides across vast mountainous regions. The earthquake triggered enormous tsunamis that spread across the entire Pacific Ocean, traveling 9,000 miles to reach California and demonstrating the global reach of seismic events. Communities across Chile were devastated, with thousands killed and countless others left homeless and traumatized by the catastrophe. The disaster reshaped our understanding of earthquake magnitudes and the plate tectonic processes that generate such tremendous force. Scientists studying the event gained crucial insights into how the Earth's crust behaves during extreme stress conditions. This earthquake remains a benchmark event that all subsequent seismic research and prediction efforts are measured against. The 1972 blizzard in Iran lasted for only 7 days, but somehow managed to kill approximately 4,000 people, making it one of the deadliest winter storms ever recorded despite its brief duration. Massive amounts of snow fell continuously across the landscape, accumulating so rapidly that villages and towns became completely buried and unreachable. Temperatures plummeted to deadly levels as wind speeds increased, creating conditions where exposed skin froze within minutes of exposure. Communities were cut off from all outside help, with no way to receive food, medicine, or rescue assistance as the storm raged relentlessly. Livestock froze in fields and pastures, compounding the humanitarian crisis as food supplies dwindled and starvation began to set in. Survivors huddled in shelters with limited fuel and dwindling supplies, facing the very real possibility that they might not survive until the storm finally ceased. When rescuers finally reached affected areas, they discovered scenes of devastating loss and profound human suffering on a massive scale. Approximately 90% of avalanche deaths occur when the victims themselves or their companions trigger the very disaster that kills them, revealing a profound truth about how human judgment becomes fragile and unreliable in the presence of mountainous terrain and dangerous slopes. People who spend their lives in mountains often develop a false sense of security, believing their experience and expertise can protect them from nature's unpredictable fury. Yet avalanches care nothing for experience or confidence, respecting only the physical laws that govern snow accumulation and gravitational force. Some climbers learn this lesson through near-death experiences that haunt them for the rest of their lives. Others never live to share their hard-won wisdom with future generations. This pattern suggests that self-caused avalanche deaths may represent a fundamental human struggle to recognize our own limitations. The mountains teach harsh lessons to those willing to listen, but many refuse to hear the warnings until it is far too late. Of avalanche victims who are buried and then rescued within just 15 minutes of being trapped, an extraordinary 93% manage to survive the ordeal, demonstrating that time becomes the crucial factor determining life and death in these catastrophes. Yet survival rates plummet dramatically as time passes, and after 45 minutes buried beneath the snow, only 20 to 30% of victims are still alive when rescuers reach them. This narrow window of survival emphasizes the brutal mathematics of avalanche rescue and the precious seconds that separate survival from tragedy. Some victims are rescued by companions who dig frantically through snow and debris, racing against the relentless clock. Others are found by professional rescue teams who arrive with trained dogs and specialized equipment, working with desperate urgency. The statistics paint a clear picture of why avalanche prevention and early detection are so important. Every minute becomes an eternity when life hangs in the balance beneath meters of compacted snow and ice. There are approximately 1,900 active volcanoes distributed across the surface of our planet, yet an astonishing 90% of them are concentrated in a single crescent-shaped zone called the Ring of Fire that encircles the entire Pacific Ocean basin. This ring traces the boundaries where tectonic plates collide and overlap, creating zones of tremendous geological instability and volcanic activity. Some volcanoes in this ring erupt with terrifying regularity, while others lie dormant for centuries before suddenly awakening with catastrophic force. Others have been sleeping for thousands of years, their peaks rising peacefully into clear blue skies while tourists hike their slopes unaware of the molten rock beneath their feet. This concentration of volcanic activity reminds us that the Earth's crust is not a stable, solid shell, but rather a dynamic system constantly shifting and reforming. The Ring of Fire represents one of the most geologically active regions on our planet, a place where the raw power of geological processes is constantly on display. Volcanic lava can reach temperatures around 2,000 degrees Fahrenheit, a level of heat so extreme that it can melt most common metals and transform solid rock into flowing rivers of destruction that obliterate everything in their path. When lava emerges from volcanic vents deep within the earth, it carries this tremendous thermal energy outward, consuming forests and reshaping landscapes in its relentless advance downhill. Some lava flows move slowly enough that people can escape them, while others advance with frightening speed, trapping those who underestimate their velocity. The heat itself becomes a weapon, igniting anything flammable at great distances from the flow itself. Survivors of lava flows report the terrible sensation of being cooked alive by radiant heat while desperately fleeing the advancing molten rock. Others describe the surreal experience of watching their homes and possessions melt and burn before their eyes in moments. Lava reminds us that temperature itself can be transformed into a destructive force that obliterates human structures and dreams. The 1906 San Francisco earthquake caused considerable destruction through the violent shaking itself, but the subsequent 3-day fire that burned throughout the city actually destroyed far more buildings and structures than the earthquake's direct impact, transforming the disaster into something even more catastrophic than the initial seismic event. The combination of damaged infrastructure, broken gas lines, and fires spreading unchecked through wooden buildings created a perfect storm of destruction. Fire departments were overwhelmed and ineffective, unable to control the flames as they spread from block to block, consuming everything in their path. Some neighborhoods were dynamited to create fire breaks, yet the flames seemed unstoppable and relentless in their advance. Survivors emerged from shelters to find their entire city transformed into a smoking wasteland of ash and ruins. The disaster revealed that earthquakes themselves are only half the story of seismic catastrophe. In many cases, the secondary fires and collapses cause far more death and destruction than the initial shaking itself. Hurricanes, typhoons, and cyclones are in fact identical meteorological phenomena that are born and behave according to the same physical principles, with the only difference being their geographic location and the names used locally to describe them. A hurricane in the Atlantic Ocean is a typhoon when it crosses the international date line into the western Pacific. That same storm would be called a cyclone if it occurred in the Indian Ocean or South Pacific region. Some people spend their entire lives believing these are 3 completely different types of storms. Others learn that the distinctions are purely linguistic rather than meteorological. Understanding this truth reveals the arbitrary nature of human naming systems applied to natural phenomena. These storms operate according to universal laws of physics, regardless of what name humans have assigned to them. The terminology teaches us that our categories and classifications often reflect human convenience rather than fundamental differences in nature itself. To be officially classified as a hurricane, a tropical cyclone must sustain wind speeds of at least 74 miles per hour for a continuous period, a threshold determined by meteorologists to distinguish these most severe tropical storms from lesser cyclones and tropical depressions. Storm systems that fail to reach this wind speed threshold remain officially unclassified as hurricanes despite potentially causing significant damage and loss of life. Some storms hover just below this threshold for extended periods, teasingly close to official hurricane status. Others rapidly intensify and cross the threshold within hours, transitioning from tropical storm to hurricane status almost overnight. The wind speed serves as a clear, objective measure that removes ambiguity from classification systems. Meteorologists rely on these categories to communicate storm severity and direct public response measures. This seemingly arbitrary threshold actually reflects real changes in storm behavior and destructive potential that occur around 74 miles per hour. Hurricane Audrey in 1957 generated a storm surge so powerfully destructive that it penetrated inland for a distance of 25 miles beyond typical coastal boundaries, inundating regions that should have been safe from ocean water based on previous historical experience. The surge pushed freshwater lakes inland and mixed saltwater deep into agricultural regions, rendering farmland unusable and contaminating water supplies for vast populations. Some communities in the affected regions experienced flooding that lasted for weeks, with water slowly draining back toward the ocean in an extended process of recovery. Others faced permanent saltwater contamination of groundwater aquifers that supplied drinking water to thousands of people. The surge demonstrated that storm surge distance is often underestimated when planning coastal defenses and evacuation chutes. Disaster planners learned from Hurricane Audrey that historical surge levels cannot be relied upon to predict maximum future surge potential. Modern coastal planning now incorporates larger safety margins based on data from extreme events like Hurricane Audrey. The largest hailstone ever documented in the United States exceeded 7 inches in diameter and weighed nearly 2 pounds, a projectile so massive that it seemed more like falling rock than frozen precipitation, falling from a single thunderstorm cell that generated unusually large crystals through powerful updrafts. The hailstone was so large that it would cause severe injury or death to anyone struck directly by it. Such enormous hailstones form when thunderstorm updrafts are extraordinarily powerful, carrying raindrops far aloft into freezing air where they accrete layer upon layer of ice. Some thunderstorms generate thousands of smaller hailstones simultaneously, each capable of destroying crops and shattering windows across entire regions. Others produce only a few truly large stones that nevertheless cause impressive damage when they strike. The formation of giant hailstones requires precise atmospheric conditions that occur rarely and unpredictably. This record-breaking hailstone serves as evidence that nature continually exceeds human expectations regarding what is physically possible. Tornadoes have been recorded in all 50 United States, demonstrating that this phenomenon, while seemingly concentrated in specific regions, actually poses a threat across the entire nation wherever atmospheric conditions align to produce rotating updrafts. However, Tornado Alley in the Central Plains, states, and Florida experiences the overwhelming majority of these violent, rotating columns of air that descend from supercell thunderstorms. Some tornadoes strike the same regions repeatedly across decades, establishing patterns that allow meteorologists to predict vulnerable areas. Others appear without warning in regions where they are uncommon, catching populations off guard and unprepared for their destructive potential. The variation in tornado frequency across the nation reflects differences in geography, climate patterns, and atmospheric dynamics. Understanding that tornadoes can occur almost anywhere emphasizes the need for public preparedness and awareness across the entire country. Tornado Alley remains the most dangerous region, yet no part of America is truly safe from the threat of these rotating storms. The Great Chicago Fire of 1871 remains one of history's most destructive urban fires, though its actual origins remain shrouded in legend rather than confirmed by reliable historical evidence. with popular stories contradicting documented facts and expert analysis. The fire occurred during a period of severe drought when wood structures dominated the cityscape and firefighting capabilities were limited compared to modern standards. Some accounts blame the fire's start on a cow kicking over a lantern belonging to a woman named Mrs. O'Leary, a story so memorable that it became embedded in popular culture. Others point to documented evidence suggesting the fire started in a lumber yard some distance from the O'Leary property. The uncertainty regarding origins reflects the challenges historians face in reconstructing events from historical records that are often incomplete or contradictory. Modern fire investigations would resolve the question definitively, yet the historical record remains ambiguous. The Great Chicago Fire reminds us that even major historical events can have their origins lost to time and incomplete documentation. In 2017, Hurricane Harvey established an unprecedented rainfall record for a single storm system in the entire history of the United States, dumping extraordinary amounts of water across Texas and Louisiana in a relentless display of nature's capacity to transform atmospheric moisture into devastating floods. The rainfall was so extreme that it exceeded anything previously recorded by historical meteorological databases and weather monitoring systems. Some regions received more rain in a single week than they typically receive in an entire year of normal weather patterns. Others experienced flash flooding that destroyed homes and displaced families from neighborhoods where they had lived for generations. The storm's water slowly receded over weeks and months, leaving behind destruction and contamination in its wake. Environmental damage extended far beyond the immediate flooding, with contaminants and debris spreading through waterways and ecosystems. Hurricane Harvey reminded communities that extreme precipitation represents a fundamental threat that climate change may intensify in coming decades. Earthquakes large enough to be felt without any instruments whatsoever occur at a rate of approximately 50,000 times annually across the entire surface of the planet, yet most strike in unpopulated regions where they cause no death, no destruction, and no human suffering. The Earth's crust is constantly in motion, with tectonic plates shifting, grinding, and colliding in perpetual geological activity. Some earthquakes release their energy gradually over extended periods, manifesting as harmless tremors. Others accumulate stress for years or centuries before suddenly rupturing in violent releases of pent-up force. The vast majority of earthquakes are too weak to cause any structural damage or even to be perceived by humans through their normal senses. Scientists detect these imperceptible tremors using sensitive seismographic instruments scattered across the world. Understanding that the Earth experiences constant seismic activity helps contextualize why major earthquakes, while terrifying, remain relatively rare events in human experience. The 1976 Tangshan earthquake in China killed approximately 300,000 people in an instant, striking a heavily populated industrial city with little or no warning, transforming a thriving urban center into a landscape of rubble and devastation in mere seconds. The earthquake's magnitude measured 7.9, strong enough to reduce most buildings to twisted metal and broken concrete. Entire blocks of apartment buildings collapsed simultaneously, trapping residents under tons of debris and condemning countless families to death in the darkness beneath the wreckage. Some survivors were found days later, still trapped but alive, their rescues celebrated amid overwhelming tragedy. Others perished silently in the dust and darkness, their families never knowing exactly where or when they had breathed their last. The Tangshan earthquake remains one of history's most devastating seismic events and demonstrates the frightening consequences of major earthquakes striking populated cities. Industrial cities built with unreinforced construction are particularly vulnerable to collapse during intense seismic activity. Between the years of 2000 and 2012, natural disasters caused approximately $1.7 trillion in economic damage worldwide and affected an astounding 2.9 billion human beings, reshaping entire economies and forcing nations to redirect resources toward recovery and rebuilding efforts. This period witnessed an increasing trend in both the frequency and severity of natural disasters across multiple geographic regions. Some economists attribute this increase to climate change and environmental degradation that destabilize weather systems. Others point to growing urbanization and increasing population density in vulnerable regions like coastal areas and floodplains. The economic toll of disasters extends far beyond immediate reconstruction costs, affecting global trade, insurance markets, and long-term development prospects. Insurance companies struggle to manage increasing claims as disasters become more frequent and severe. The financial burden of natural disasters falls disproportionately on developing nations that lack resources for recovery and adaptation. Flooding is now classified as the costliest natural disaster on the entire planet in terms of pure economic losses, surpassing even earthquakes and devastating hurricanes in total financial impact to human economies and infrastructure. Floods cause damage to buildings, infrastructure, agricultural land, and industrial facilities on a massive scale that extends across entire regions. Some floods persist for months, preventing any economic activity and forcing prolonged evacuations that compound the disaster's economic consequences. Others recede more rapidly, but leave behind contamination and debris that requires expensive cleanup and remediation efforts. The agricultural losses from flooding are particularly severe, as floods destroy crops before they can be harvested and contaminate soil with salt water or debris. Floods also increase disease transmission through contaminated water supplies, adding health costs to the already substantial economic burden. The true cost of flooding extends far beyond what economists can easily calculate, affecting both tangible infrastructure and intangible human well-being. The Earth has lost more than 28 trillion tons of ice in recent decades, contributing significantly to rising sea levels that increase flood vulnerability in coastal communities worldwide, threatening cities and regions that have been inhabited by humans for thousands of years. This ice loss accelerates annually as global temperatures continue to increase, representing one of the clearest indicators of changing climate conditions. Some glaciers have retreated so dramatically that they no longer exist in locations where they were present just decades ago. Others are shrinking at rates that seem almost impossible to reconcile with human timescales of perception. The melting ice releases fresh water into the oceans, changing salinity levels and disrupting marine ecosystems that depend on precise chemical conditions. Coastal cities that have survived for centuries with stable sea levels now face the prospect of permanent inundation as water levels continue their inexorable rise. The loss of glacial ice represents a slow-motion catastrophe playing out across years and decades rather than moments. In 2022, the United States experienced 68,988 separate wildfire incidents that burned a total of 7,500,000 577,183 acres of land, with over 40% of the burned acreage occurring in western states where drought conditions have intensified. Wildfires consume forests that took centuries to grow, destroying habitats and burning away carbon that was sequestered in tree trunks and root systems. Some wildfires spread so rapidly that they trap residents who underestimated the danger and attempted to flee too late. Others move slowly enough that communities have days to evacuate and prepare for potential impact. The smoke from massive wildfires travels thousands of miles, affecting air quality in distant cities and causing respiratory problems in populations far from the actual fire. Wildfire seasons have grown longer and more intense as climate conditions change and precipitation patterns become less predictable. The increasing frequency of massive wildfires suggests that the balance between fire suppression efforts and natural fire occurrence has fundamentally shifted. Climate change is increasing the frequency and intensity of natural disasters, particularly hurricanes, devastating droughts, and extreme flooding events that impact vulnerable regions with growing regularity and severity. Scientific evidence accumulated over decades now clearly demonstrates this connection between warming global temperatures and increasingly extreme weather phenomena. Some regions that previously experienced mild weather patterns now regularly encounter conditions approaching extreme disaster thresholds. Others that traditionally endured harsh conditions face intensification of already severe natural hazard environments. Monsoon patterns are shifting, causing droughts where rains once fell reliably and floods where dryness once prevailed. Ocean temperatures are warming, providing more energy for hurricane intensification and potentially allowing hurricanes to reach unprecedented strength levels. The connection between climate change and natural disaster intensity has become clearer with each passing year of observational data and scientific analysis. The 2008 Sichuan earthquake in China measured 7.9 on the Richter scale and resulted in the deaths of nearly 90,000 people across the region, including thousands of students who perished when schools collapsed during the devastating seismic event. The earthquake occurred with little warning, striking during daylight hours when many children were attending school in buildings not designed to withstand major seismic activity. Many of the collapsed school buildings suggested poor construction practices and inadequate building codes that failed to ensure seismic safety. Survivors emerged to face the anguish of searching for loved ones amid rubble and wreckage that stretched across the landscape. Some families were never reunited with missing relatives, their fates unknown or discovered weeks later in mass graves. The disaster sparked protests and investigations into construction practices and building code enforcement. The Sichuan earthquake remains a sobering reminder that earthquakes pose particular dangers to children in schools that may not be properly engineered for seismic safety. Landslides triggered by earthquakes or heavy rainfall can isolate affected regions by destroying transportation routes and communication infrastructure, leaving populations without electrical power, telephone communication, or any reasonable access to emergency medical resources for weeks or even months. The isolation compounds the humanitarian crisis, preventing rescue teams and aid workers from reaching survivors who desperately need food, water, medicine, and medical treatment. Some communities cut off by landslides have experienced famine and disease outbreaks that killed as many people as the initial disaster itself. Others suffered through winters without adequate fuel for heating, with inadequate shelter protection against cold and snow. The psychological toll of isolation adds to the physical hardships as people wonder whether rescue efforts will ever arrive or if they have been forgotten by the outside world. Modern transportation networks often concentrate on routes that are vulnerable to landslide damage, making these communities particularly fragile. Landslides reveal how dependent modern societies are on reliable infrastructure and transportation routes that nature can destroy, with little regard for human inconvenience. Hurricane Katrina in 2005 caused approximately $161 billion in total damages, making it the costliest hurricane in the entire recorded history of the United States and one of the most devastating natural disasters that the nation has ever experienced. The hurricane devastated New Orleans particularly severely, with levee failures allowing floodwaters to inundate the city far beyond predictions and emergency planning scenarios. Some neighborhoods in New Orleans were completely submerged for weeks, with buildings and infrastructure suffering total destruction. Others experienced partial flooding and contamination that made them uninhabitable and required extensive remediation and reconstruction efforts. The hurricane's disruption of commerce in the Gulf of Mexico region had ripple effects extending far beyond the disaster zone, affecting national economy and energy supplies. The human toll included approximately 1,800 deaths and countless cases of displacement and psychological trauma. Hurricane Katrina demonstrated that even wealthy, developed nations remain vulnerable to catastrophic natural disasters that overwhelm emergency management systems. The failure of dikes and levees during the catastrophic Hurricane Katrina resulted in more than 1,800 deaths across Louisiana, Alabama, Florida, Georgia, and Mississippi, transforming entire communities into desolate landscapes of abandonment and devastation. Long ago, engineers built these protective barriers with the assumption that they would withstand the worst storms history had produced. Yet nature exceeded those predictions with terrible force. The levees failed not only from the storm surge itself, but also from poor maintenance and inadequate funding that had been neglected for decades. Over time, the systems degraded and weakened, becoming more fragile with each passing year of delayed repairs and budget cuts. Even now, communities struggle to recover from the failures that left them vulnerable to the rising water. The psychological damage to residents who lost everything and faced the reality that their protective infrastructure was inadequate added layers of trauma beyond the physical destruction. The levee failures represented human negligence, compounding natural disaster into something far more catastrophic. Hurricane Katrina also triggered a sequential chain of 59 separate tornado formations within just 6 days as the storm system moved across 9 different states, demonstrating how one natural disaster can cascade into multiple secondary catastrophic events that amplify the overall damage and destruction. Long ago, meteorologists understood that hurricanes could spawn tornadoes, yet the sheer number triggered by Katrina exceeded most prediction models and expectations. These tornadoes added devastating impacts across regions far from the storm's center, spreading destruction across a wider geographic area. Over time, meteorological models improved their ability to predict tornado formation during hurricane passages, thanks to data collected from events like Katrina. Some of the tornadoes were brief and relatively minor, causing localized damage in limited areas. Others were violent and long-lived, tracking across multiple counties and causing destruction comparable to the hurricane's own effects. The tornado outbreak reminded scientists that hurricanes represent more complex threats than the primary wind and rain systems. Hurricane Maria in 2017 struck Puerto Rico as a catastrophic Category 5 hurricane, the strongest classification on the hurricane severity scale, leaving the entire island completely without electricity in what became the largest blackout in all of United States history, affecting over 3 million people simultaneously. Long ago, power grids were designed to withstand typical hurricane-force winds, yet Maria's intensity exceeded design specifications and destroyed generation and distribution infrastructure across the entire island. The island's vulnerable location in hurricane-prone waters meant that Maria was not an unexpected event in a statistical sense, yet the severity exceeded historical precedent. Over time, the power restoration process moved frustratingly slowly, with months passing before even partial service returned to most communities. Even now, years later, Puerto Rico continues to rebuild infrastructure damaged by the hurricane. The prolonged blackout affected hospitals, water treatment facilities, refrigeration systems, and communication networks that communities depend upon for basic survival needs. The extended power outage demonstrated how hurricanes can create humanitarian crises that extend far beyond the direct storm impacts. The 2010 Haiti earthquake killed approximately 316,000 people and devastated the nation's already fragile infrastructure and healthcare systems beyond the capacity for immediate repair or restoration, leaving the poorest nations to face the cruelest consequences. Long ago, Haiti had experienced significant infrastructure decline due to decades of political instability and limited economic development. The earthquake struck a nation already struggling with poverty and limited resources, compounding human suffering exponentially. Over time, international aid arrived, yet the scale of destruction exceeded the capacity of any single nation or organization to address comprehensively. Some neighborhoods were simply abandoned after the earthquake, with residents relocating rather than attempting reconstruction. Others witnessed extraordinary efforts by both local residents and international volunteers attempting to rebuild amid overwhelming challenges. The Haiti earthquake demonstrated that earthquake impacts depend not only on magnitude, but also on the vulnerability of the populations affected. The Antioch earthquake of 526 in the Byzantine Empire, in what is now modern Turkey, killed approximately 300,000 people in one of history's deadliest recorded seismic events, indicating that catastrophic earthquakes have been reshaping human civilizations for millennia. Long ago, ancient cities were built without knowledge of earthquake-resistant construction principles or seismic safety standards that modern engineers take for granted. Antioch was a major city of its era, densely populated and built with materials that could not withstand major seismic shaking. Over time, historical records of the earthquake survived in written documents that preserve knowledge of the disaster for posterity. Some of the survivors witnessed the complete transformation of their city in mere moments of violent shaking. Others perished silently beneath collapsed buildings that entombed them forever. The Antioch earthquake reminds us that catastrophic seismic events have always threatened human populations throughout recorded history. The Ganja earthquake of 1139 in the Seljuk Empire in present-day Azerbaijan killed approximately 230,000 people, indicating that major earthquakes have continued to claim enormous death tolls across many centuries and diverse geographic regions. Long ago, the Seljuk Empire was a powerful regional power, yet remained vulnerable to the raw forces of geological upheaval. The earthquake struck without warning, as all earthquakes do, destroying cities and reshaping the political landscape through the deaths of vast populations. Over time, survivors rebuilt their communities, and civilizations continued despite the tremendous losses inflicted by nature. Some regions recovered within generations, while others took centuries to regain their previous prosperity and population levels. Even now, the memory of such catastrophes serves as humbling reminders of human fragility before natural forces. The Ganja earthquake demonstrates that major seismic disasters have been recurring phenomena throughout the entire span of recorded history. The Haiyuan earthquake of 1920 in China killed approximately 273,000 people across the affected region, representing another chapter in the long history of catastrophic seismic events that have shaped human civilizations throughout recorded time. Long ago, the earthquake struck with the same sudden violence that characterizes all major seismic events, without warning or opportunity for human response. The affected region experienced widespread destruction of buildings and infrastructure that took decades to fully repair. Over time, reconstruction efforts proceeded slowly, with limited resources and technology to support rapid recovery. Some communities were rebuilt in locations displaced from their original sites, creating new urban centers. Others were essentially abandoned as survivors relocated to more fortunate regions untouched by the disaster. The Haiyuan earthquake contributes to the historical record of seismic disasters that demonstrates their recurring nature and the consistency of their devastating impacts. Volcanic eruptions can inject massive quantities of ash and aerosol particles into the upper atmosphere, creating layers of fine dust that persistently block incoming solar radiation and cause global temperature decreases that affect agricultural yields and food production worldwide. Long ago, major volcanic eruptions were followed by years of cooler temperatures that damaged crop production and triggered widespread famine. Scientists studying ice cores and historical records have documented multiple instances of volcanic-induced temperature decreases and their impacts on human populations. Over time, the mechanism of volcanic cooling became understood through research into volcanic emissions and atmospheric physics. Some volcanic eruptions in recorded history triggered famines that killed more people than the eruptions themselves. Others had limited global impact despite being locally catastrophic events. Even now, scientists recognize that a sufficiently large volcanic eruption could trigger years of reduced crop production and food scarcity. The Ring of Fire accounts for approximately 90% of the world's actively erupting volcanoes, concentrating tremendous geologic instability and volcanic hazards within a crescent-shaped zone that encircles the entire Pacific Ocean basin and affects dozens of countries. Long ago, volcanic activity in the Ring of Fire shaped landscapes and created the geographic features that define the region's character. The concentration of volcanoes reflects fundamental plate tectonic processes that cannot be altered by human intervention or engineering. Over time, populations have settled in the Ring of Fire regions despite the obvious volcanic hazards drawn by fertile volcanic soils and access to fisheries. Some communities have learned to coexist with volcanic hazards through evacuation planning and construction techniques. Others have suffered catastrophic losses when volcanoes erupted after centuries of dormancy. The Ring of Fire serves as a geographic reminder that volcanism remains an active geological process on our dynamic planet. Tsunamis travel across ocean basins at extraordinary speeds, reaching 500 miles per hour in deep water. Yet they create waves only a few feet high in the open ocean that pass beneath ships almost unnoticed before traveling vast distances to strike distant shores. Long ago, ancient mariners were sometimes unaware of tsunamis passing beneath their vessels because the waves were too small to produce noticeable disturbances in deep water. Yet the same tsunami that passes silently beneath a ship at sea transforms into a devastating wall of water when it approaches shallow coastal regions. Over time, understanding of tsunami physics improved as scientists documented the relationship between water depth and wave behavior. Some of the oldest recorded tsunamis were described in ancient texts that observers only recognized as unusual in retrospect. Others were more obviously catastrophic from the moment they struck. The physics of tsunami propagation demonstrates how the same phenomenon can produce dramatically different consequences depending on geographic context and water depth. When tsunamis reach shallow coastal waters following their long transoceanic journey, they decelerate dramatically due to friction with the seafloor, yet simultaneously compress and grow exponentially in height, sometimes reaching 100 feet or more at the actual shoreline and delivering devastating energy. Long ago, coastal communities were sometimes surprised by tsunamis that seemed to appear from nowhere with little warning, as the deep water face of the tsunami provided few obvious signs. Scientists studying tsunami behavior have documented numerous instances where coastal areas experienced dramatic water level drops, followed moments later by surging walls of water. Over time, early warning systems have been developed that can detect earthquakes and predict tsunami arrival times, providing precious minutes of warning. Some modern tsunamis have been met with evacuations based on warnings, saving thousands of lives. Others continue to strike unprepared populations in regions lacking warning systems and evacuation plans. The vulnerability of coastal populations to tsunamis persists, despite our scientific understanding of how they form and travel. The Karinga cyclone of 1839 in India generated massive waves, standing 40 meters tall, that completely destroyed the harbor and devastated the surrounding region, with a death toll estimated at 300,000 souls lost in just a few terrifying hours. Some people were caught by the waves while working in the harbor, suddenly swept away by water that rose higher than most buildings. Others perished in their homes as the ocean surged far inland, carrying away everything they had built and cherished. The cyclone's power seemed almost supernatural to those who witnessed it, as if the sea itself had decided to wage war against the land. This reminds us that cyclones remain among the deadliest natural disasters, capable of claiming enormous death tolls in single events. The survivors emerged into a transformed landscape where familiar places had become unrecognizable. Even now, the memory of such cyclones serves as a reminder of the sea's awesome and terrible power. The 1931 flood of the Yellow River in China resulted in approximately 2 million deaths, making it one of the deadliest natural disasters in recorded history, a tragedy so immense that it affected an entire quarter of the nation's population. Some people drowned in the initial surge, while others perished from disease and starvation in the months that followed. Others were displaced from their homes and forced to wander as refugees seeking higher ground and safety. The inundation lasted for months, with water persisting across vast regions and preventing any normal economic activity or food production. This reminds us that floods can be not merely momentary events, but extended catastrophes that compound over time. The survivors faced immense suffering as they attempted to rebuild their lives from nothing. Even now, this flood remains a benchmark of the worst-case scenarios for flood disasters. The 1920 Haiyuan earthquake in China killed approximately 273,407 people in widespread seismic destruction across the affected region. Some areas experienced complete building collapse, where thousands of residents perished simultaneously in the darkness. Others suffered partial damage that still rendered communities uninhabitable for extended periods of recovery. The earthquake reminded people that solid ground offers no true safety against seismic forces. This reminds us that earthquakes have been reshaping human civilizations throughout recorded history. Survivors faced the grim task of searching through rubble for family members whose fate remained unknown. Even now, the earthquake serves as historical testimony to earthquake dangers. The 1139 Ganja earthquake in the Seljuk Empire in present-day Azerbaijan killed approximately 230,000 people, indicating that catastrophic earthquakes have struck various regions across different cultures and civilizations. Some survivors fled the region entirely, seeking refuge in distant lands where earthquake danger seemed less immediate. Others remained and rebuilt their communities despite the trauma and loss. The earthquake's violence was indiscriminate, affecting rich and poor equally in its destructive power. This reminds us that earthquake danger is not unique to any single geographic region, but rather distributed globally. The written records of this earthquake have survived through centuries, preserving knowledge of the disaster. Even now, historical documentation of ancient earthquakes helps modern scientists understand seismic patterns. Volcanic eruptions can inject massive quantities of ash into the atmosphere, blocking sunlight and causing global temperature decreases that affect agricultural yields and food production across entire continents and regions. Some eruptions produce so much ash that they darken the sky for months, creating a perpetual twilight across wide areas. Others are less dramatic, yet still alter climate patterns enough to damage crops and trigger famine. Ash that falls from the sky contaminates water supplies and damages machinery and equipment. This reminds us that volcanic impacts extend far beyond the region where the eruption occurs. The global effects can be subtle, yet devastating to populations dependent on consistent weather patterns. Even now, scientists monitor large volcanoes, aware of their potential to alter planetary climate. The Ring of Fire accounts for approximately 90% of the world's active volcanoes, concentrating tremendous geologic instability in a crescent-shaped zone that encircles the Pacific Ocean basin and affects dozens of countries simultaneously. Some volcanoes in this ring erupt regularly on timescales measurable in years or decades. Others remain dormant for centuries before suddenly awakening with tremendous force. The concentration reflects fundamental plate tectonic processes that occur at the boundaries between major crustal plates. This reminds us that volcanic hazards are not randomly distributed, but rather concentrated in specific geographic zones. Communities within the Ring of Fire face persistent volcanic threats despite living in otherwise desirable locations. Even now, the ring remains the most volcanically active zone on our dynamic planet. Tsunamis can strike coastal communities without warning, sometimes arriving within minutes of the seismic event that triggered them, leaving little time for evacuation or preparation before the waves crash ashore with devastating force. Some coastal residents receive no warning at all when distant earthquakes trigger tsunamis that travel toward their shorelines. Others benefit from modern warning systems that provide precious minutes to evacuate inland to higher ground. The speed of tsunami. Travel means that the ocean can carry destruction across vast distances almost instantaneously on a human timescale. This reminds us that distance provides no protection against tsunami hazards in an interconnected world. Survivors of tsunamis describe the experience as nightmarish and surreal beyond comprehension. Even now, coastal populations remain vulnerable to distant earthquakes that may trigger deadly tsunamis. When tsunamis reach shallow coastal waters, they slow dramatically but compress and grow exponentially in height, sometimes reaching 100 feet or more at the shoreline and delivering devastating energy to coastal communities. Some tsunamis announce themselves with a dramatic recession of ocean water that exposes the seafloor. Others arrive as sudden surges without preliminary warning signs that might allow people to prepare. The physical power of tsunami waves is capable of moving buildings, destroying infrastructure, and reshaping coastlines permanently. This reminds us that the most destructive events often occur when deep ocean forces interact with shallow coastal geography. Survivors describe being swept away by water that seemed impossible to resist or escape from. Even now, research continues into how coastal defenses might be improved to withstand tsunami impacts. Tsunamis can travel across ocean basins at speeds reaching 500 miles per hour in deep water, yet they create waves only a few feet high in the open ocean that pass beneath ships almost unnoticed before traveling vast distances to strike distant shores. Some ancient mariners never realized they had passed beneath a tsunami while their ship remained largely unaffected by the barely perceptible wave. Others documented strange water level changes that only later were understood to be tsunamis passing through deep ocean. The contrast between deep ocean and coastal behavior reveals the complex physics of wave propagation. This reminds us that the same phenomenon can produce dramatically different consequences depending on geographic context. The transformation from imperceptible wave to devastating destruction occurs across relatively short distances. Even now, this principle guides tsunami warning systems that detect deep ocean disturbances. Approximately 90% of avalanche fatalities occur when victims or their companions trigger the very disaster that kills them, revealing something profound about how human judgment becomes fragile in mountainous terrain. Some avalanche victims survived earlier avalanches, but miscalculated the conditions during the later events. Others ignored warnings and proceeded into obviously dangerous terrain driven by overconfidence or necessity. The snow itself becomes a weapon that responds to weight and disturbance by releasing its stored energy. This reminds us that mountains are not tamed spaces, but rather retain their wild nature regardless of human skill and experience. Survivors who witness companions buried in avalanches often experience trauma that haunts them forever. Even now, avalanche education emphasizes understanding how human actions can trigger the very disasters that kill. Of avalanche victims buried and then rescued within just 15 minutes, an extraordinary 93% survive. Yet after 45 minutes underground, only 20 to 30% remain alive when rescuers finally reach them. Some rescue teams work with remarkable speed to locate and excavate trapped victims before oxygen depletion becomes fatal. Others arrive to find victims who have already perished in the suffocating darkness beneath compacted snow. The narrow window of survival emphasizes that time becomes the most precious resource in avalanche rescue operations. This reminds us that avalanche survival depends partly on luck and partly on rapid rescue response. The mathematics of oxygen depletion and blood oxygen saturation drive the harsh reality of avalanche rescue. Even now, avalanche rescue training emphasizes rapid response and efficient burial depth estimation. Wildfires spread through forests and grasslands, consuming vegetation that took decades or even centuries to grow, fundamentally altering ecosystems and habitats for countless species that depend on mature forests for survival. Some forests have evolved to exist with periodic fires, yet those cycles are being disrupted by intensifying heat and changing rainfall patterns. Others have no natural fire history and remain uniquely vulnerable when flames arrive. The vegetation burns away, releasing carbon into the atmosphere that was locked within living biomass for generations. This reminds us that forests represent accumulated growth across long time scales that fire can obliterate in moments. The ash settles on the soil, enriching it with nutrients, yet also leaving behind scorched earth and widespread devastation. Even now, survivors speak of the strange and haunting beauty of landscapes transformed by fire into unrecognizable terrain. Droughts persist for years, gradually depleting water resources and emptying the soil of moisture that plants depend upon to survive and grow strong through seasons of increasing aridity. Some droughts develop slowly over years, creating progressive stress that communities attempt to manage through conservation and rationing. Others arrive suddenly when rainfall patterns shift from abundant to minimal with little transition. The soil becomes hardened and cracked, unable to support vegetation that requires moisture to germinate and flourish. This reminds us that water is precious and finite, flowing through seasonal cycles that sometimes bring abundance and sometimes bring scarcity. Crops wither in fields, livestock starve when pastures dry to dust, and drinking water becomes impossibly scarce. Even now, communities in drought-affected regions develop deeper appreciation for water's essential nature to all life. Earthquakes continue to evolve slowly over geological time as tectonic plates move imperceptibly beneath our feet, storing and releasing tremendous energy through sudden violent ruptures that reshape landscapes in moments. Some earthquakes are preceded by foreshocks that scientists can detect but rarely predict with precision regarding magnitude or timing. Others strike without warning, with no detectable foreshocks to alert populations of coming danger. The plates grind and slip, overcoming friction through accumulation of stress that builds across decades or centuries. This reminds us that the ground beneath us is not stable, but rather alive with movement operating on geological timescales. The stored elastic energy releases in waves that propagate through rock, causing the shaking and destruction. Even now, seismologists monitor plate boundaries carefully, aware of the potential for major earthquakes to occur without warning. Volcanic mountains grow slowly over millions of years, accumulating layer upon layer of cooled lava and ash until they tower thousands of feet above surrounding terrain with summits reaching toward distant skies. Some volcanoes have been building for millions of years through countless eruption cycles that deposit material methodically. Others grow more rapidly when eruptions occur with greater frequency, adding height and volume through successive deposits. The mountains themselves become monuments to geological activity, visible from vast distances and attracting human communities despite the hazards. This reminds us that volcanoes represent long-term geological processes that dwarf human lifespans in their timescales. The slopes gradually steepen as material accumulates, creating spectacular landforms that inspire awe and wonder. Even now, volcanoes continue their slow growth, adding material through ongoing eruptions that shape the landscape imperceptibly. Some earthquakes wander far from where they were predicted to occur, following fault lines that twist and turn through the Earth's crust in unexpected patterns and directions that confuse prediction models. Some seismologists spent years studying one fault only to discover that major earthquakes occurred on previously unknown parallel faults. Others found that earthquakes triggered distant quakes through stress transfer mechanisms that operate across significant distances. The fault lines represent zones of weakness where plate movements concentrate their stress and release energy. This reminds us that geological systems operate according to principles that remain incompletely understood despite centuries of scientific study. The ruptures follow paths determined by rock strength and stress orientation rather than human expectations. Even now, seismologists work to understand fault systems and improve earthquake prediction accuracy. Floods recycle water across landscapes, carrying sediment and nutrients that reshape valleys and deposit rich soils that become fertile agricultural regions over extended periods of time. Some floods bring destruction, yet also bring renewal as sediment deposition replenishes farmland with fertile material. Others devastate entirely without providing any compensating benefit to affected regions. The water moves slowly or rapidly depending on terrain and precipitation rates, carving new channels and reshaping drainage patterns. This reminds us that water represents both a life-giving force and a destructive hazard depending on circumstances. The sediment travels downstream, eventually settling in deltas and plains, where it enriches soil for future generations. Even now, ancient flood deposits provide evidence of massive inundations that occurred thousands of years before human observation. Hurricanes form over warm tropical waters, drawing energy from heat and moisture that rise invisibly into the atmosphere to fuel their rotating circulation patterns that can span hundreds of miles. Some hurricanes develop rapidly when atmospheric conditions align perfectly, intensifying from tropical depression to major hurricane in mere days. Others move slowly across warm water, stalling over regions and drawing moisture from the ocean beneath them. The warm air rises and cools, releasing latent heat that further energizes the storm system in a self-reinforcing feedback mechanism. This reminds us that hurricanes represent natural convection systems that transfer heat from the ocean to the upper atmosphere. The Coriolis effect causes the rising air to rotate, creating the characteristic spinning patterns observed in satellite imagery. Even now, ocean temperatures rise through climate change, potentially intensifying hurricane development and intensification rates. Tornadoes emerge from thunderstorms when atmospheric conditions align perfectly, creating rotating columns of air that touch down briefly before dissolving back into the storm from which they originated. Some tornadoes develop from clear visual signatures in radar imagery that meteorologists can sometimes recognize and warn populations. Others form with minimal warning, appearing suddenly and vanishing equally quickly in ways that defy prediction. The rotation is driven by wind shear and atmospheric instability that creates favorable conditions for rotation. This reminds us that tornadoes represent atmospheric phenomena that operate on scales sometimes too small for reliable advance warning. The funnel descends from the cloud base, creating a visible condensation funnel that marks the vortex location. Even now, meteorologists study tornado development using radar data and storm-chasing observations. Hail forms when raindrops freeze in the upper atmosphere, falling and rising repeatedly through different temperature layers until they become heavy enough to descend through warmer air without completely melting. Some hailstones grow through multiple freeze cycles, accumulating concentric layers of ice that create the characteristic appearance of large hail specimens. Others form more rapidly with simpler structure and smaller ultimate size. The updrafts in supercell thunderstorms can suspend large hailstones aloft for extended periods, allowing tremendous ice accumulation. This reminds us that hail formation requires specific atmospheric conditions with strong updrafts and sufficient moisture. The hailstones eventually become too heavy to remain suspended and fall to the surface below. Even now, hail remains difficult to predict accurately, with meteorologists relying on radar signatures and atmospheric analysis to identify hail potential. Lightning strikes the Earth approximately 100 times every single second across the entire planet. Though most strikes occur over oceans where they go largely unobserved by human populations living on land. Some lightning strikes occur in visible thunderstorms directly overhead, creating dramatic and frightening displays of atmospheric electricity. Others occur kilometers away, visible as lightning in distant clouds, but beyond immediate threat. The electrical discharge occurs when charge buildup in clouds exceeds the electrical resistance of the air between cloud and ground. This reminds us that electrical processes operate constantly in our atmosphere, transferring enormous amounts of energy. The current flows through the most conductive path available, sometimes through trees or buildings or humans in the wrong place. Even now, lightning protection systems remain imperfect despite understanding of electrical phenomena. Avalanches release snow that has been accumulating patiently on mountainsides, storing potential energy in gravitational fields until a trigger causes it to release suddenly and violently down slopes. Some avalanches are triggered by obvious factors like steep slope angles exceeding the friction threshold of snow. Others release for reasons that remain mysterious even to avalanche forecasters who have studied conditions carefully. The snow contains layers of varying crystalline structure and density that affect how stress transfers through the pack. This reminds us that avalanches represent stored energy released according to physical laws that can be understood but not always predicted. The snow accelerates downslope, increasing speed as gravity pulls it toward lower elevations. Even now, avalanche research continues seeking better predictive models and warning systems. Landslides reshape hillsides by moving massive quantities of rock and soil downward, exposing new earth materials and altering the contours of mountains and valleys in ways that persist for generations. Some landslides move slowly, advancing only meters per year in imperceptible creep. Others advance rapidly, suddenly releasing accumulated stress and tumbling down slope with terrifying speed. The materials settle at the base of slopes, creating new terrain and blocking valleys with debris. This reminds us that mountains are constantly reshaping themselves through gravitational processes. The exposed Earth reveals layers of history accumulated through millions of years. Even now, landslides continue to reshape mountain landscapes in patterns that repeat across geological time. Submarine earthquakes trigger tsunamis that travel vast distances across oceans, delivering energy across entire ocean basins to strike distant coastlines hours later with waves that grow progressively larger. Some submarine earthquakes occur at subduction zones where plates collide with tremendous force. Others happen along transform faults where plates slip horizontally against each other. The seafloor displacement creates waves that radiate outward in expanding circles. This reminds us that earthquakes beneath the ocean pose hazards to distant coastal communities. The waves travel at speeds too fast to escape once detected by observers on shore. Even now, underwater earthquakes remain sources of tsunami hazard to coastal populations. Storm surge pushes ocean water inland beyond normal tidal ranges, inundating coastal communities and farmland with salt water that contaminates soil and damages infrastructure through salt deposition and saturation. Some storm surge penetrates miles inland, depositing sediment and salt that remains for years. Others recede more rapidly, yet leave behind contaminated groundwater and damaged buildings. The salt water destroys vegetation and renders land temporarily unusable for agriculture. This reminds us that oceans can reach far inland when pushed by powerful storms. The salt permeates soil layers and persists through seasons of rainfall, trying to flush it away. Even now, communities repair damage from storm surge that altered coastal ecosystems. Blizzards accumulate snow steadily over days, burying landscapes under meters of white powder and making travel and communication impossible across frozen regions isolated by the winter storms. Some blizzards arrive with little warning as wind patterns shift suddenly. Others develop gradually as cold air masses move slowly toward populated regions. The snow piles higher and higher, blocking roads and burying vehicles where they were parked. This reminds us that snow represents a natural hazard when it accumulates rapidly. The wind carries snow into drifts that form barriers to movement. Even now, blizzards continue to strand travelers and disrupt transportation networks. Dust storms sweep across deserts and plains, carrying fine particles that reduce visibility to zero and deposit sediment across vast areas of neighboring territory in ways that transform landscapes. Some dust storms advance as walls of dust hundreds of meters tall. Others spread gradually as fine particles drift downwind across great distances. The dust fills the air, coating everything with sediment that obscures the sun. This reminds us that deserts represent sources of dust that can travel vast distances. The particles settle on land and water, altering their character and coloration. Even now, dust storms continue to redistribute sediment across continents and oceans. Mudslides occur when heavy rainfall saturates soil, reducing friction between layers and allowing entire hillsides to flow downward like a thick liquid moving slowly through valleys. Some mudslides are triggered by intense rainfall lasting only hours. Others develop gradually as weeks of steady rain progressively saturate the soil. The mud flows downslope, engulfing everything in its path, with material that hardens when it stops moving. This reminds us that water reduces soil strength and promotes downslope movement. The debris accumulates at valley bottoms, where it remains as evidence of the slides. Even now, heavy rains trigger mudslides in vulnerable mountainous regions. Forest fires consume wood fibers that have been growing for centuries, releasing carbon and energy that was stored in cellular structures through photosynthesis accumulated across generations. Some fires burn slowly through undergrowth, consuming smaller vegetation while leaving mature trees standing. Others advance rapidly through dry branches and leaves, reaching tree crowns and creating intense heat. The wood burns away, releasing smoke that spreads across vast areas downwind. This reminds us that forests represent accumulated biomass susceptible to rapid consumption by fire. The ashes settle on soil, enriching it with minerals and destroying organic matter. Even now, wildfires continue to consume forests across the planet. Earthquakes remind us that the ground beneath our feet is alive, constantly moving and shifting in response to forces deep within the Earth's interior that operate beyond human perception. Some people spend their entire lives unaware that the solid ground moves beneath them. Others experience earthquakes dramatically, awakening to violent shaking that terrifies them completely. The motion persists for seconds or minutes, then ceases and returns the ground to apparent stillness. This reminds us that geological activity remains constant even when imperceptible. The stress accumulates slowly across years, eventually released suddenly. Even now, the ground continues to move in response to deep earth processes. Hurricanes remind us that the ocean and atmosphere are interconnected, exchanging heat and moisture in cycles that span seasons and reshape weather patterns globally in ways that affect distant regions. Some hurricanes form over oceans near the equator, where water temperatures are warmest. Others develop at higher latitudes where atmospheric conditions become favorable. The rotation creates characteristic spinning patterns visible in satellite imagery taken from space. This reminds us that weather systems operate on scales spanning entire ocean basins. The energy transfers between ocean and atmosphere through evaporation and condensation. Even now, hurricanes continue to form over warm tropical waters seasonally. Volcanoes remind us that the Earth's interior remains molten and dynamic, maintaining a core of superheated material that occasionally breaks through the crust and emerges as flowing lava and ejected ash. Some volcanoes erupt with warning signs that precede the main eruption by weeks or months. Others awaken suddenly from dormancy with little precursory activity. The material emerges from deep chambers beneath the surface. This reminds us that heat persists at the Earth's core despite the cool surface. The pressure builds gradually over time until release becomes inevitable. Even now, volcanic material continues to emerge from interior layers and shape surface topography. Droughts remind us that water is precious and finite, flowing through seasonal cycles that sometimes bring abundance and sometimes bring profound scarcity to regions and communities dependent on reliable rainfall. Some droughts arrive suddenly when rainfall patterns shift with little transition from wet to dry conditions. Others develop gradually as weeks and months pass without meaningful precipitation accumulating in soil and aquifers. The soil becomes hardened and cracked as moisture evaporates away into the atmosphere. This reminds us that water cycles through seasons and years in patterns humans can observe but cannot control. The vegetation withers away as roots struggle to find moisture in desiccated earth. Even now, droughts persist in regions where rainfall patterns have grown increasingly unpredictable. Tsunamis remind us that the ocean possesses tremendous power, capable of reshaping coastlines and moving enormous quantities of water across continental distances in response to seismic disturbances. Some tsunamis are triggered by earthquakes that shift the seafloor vertically, displacing water column above them. Others result from submarine landslides that suddenly release water from confined areas. The waves travel at remarkable speeds across ocean basins, transporting energy from epicenters to distant shores. This reminds us that earthquakes beneath the ocean create hazards far from where they occur. The water moves silently in deep ocean, then transforms dramatically as it approaches land. Even now, coastal populations remain vulnerable to distant underwater earthquakes. The Earth continues to evolve slowly over time as geological processes operate across millions of years in patient cycles of creation and destruction that reshape landscapes imperceptibly. Some mountains rise as tectonic forces push rock layers upward through millennia. Others erode away as water and wind slowly wear down their slopes through weathering and gravitational movement. The rocks transform from solid stone to regolith and soil through chemical and physical processes. This reminds us that geological time operates on scales vastly different from human lifespans. The landscape shifts gradually, appearing unchanging across human generations, yet fundamentally different across millions of years. Even now, geological processes continue their ancient work of reshaping the planet's surface. Some mountains wander higher as tectonic pressure accumulates, lifting them gradually toward the sky in imperceptible movements that span thousands of years and go largely unnoticed by observers. Some mountain ranges rise at measurable rates when tectonic activity intensifies in particular regions and time periods. Others remain stable for extended periods as stress accumulates slowly beneath the surface before being released. The uplift occurs as rock layers fold and fault, moving upward relative to surrounding terrain. This reminds us that mountains represent visible evidence of tectonic processes operating continuously. The peaks continue to rise even now, though the movement is typically too slow for human perception. Even now, surveyors use precise instruments to measure the subtle annual changes in mountain elevations. Earthquakes come and go, occurring regularly across the planet, each releasing energy that has been stored in crustal rocks deep beneath the surface and accumulated through years or centuries of plate movement. Some earthquakes are followed by aftershocks that continue for weeks or months as stress redistributes through rock layers. Others appear to be isolated events with no obvious preceding foreshocks or following aftershocks. The shaking propagates outward from the epicenter in expanding concentric circles that carry seismic energy across vast distances. This reminds us that earthquakes represent a constant geological process rather than rare anomalies. The fault ruptures slowly or rapidly depending on rock properties and stress conditions present at the moment of failure. Even now, countless earthquakes occur daily across the planet in mostly unpopulated areas where they cause no observable damage. Volcanoes sit quietly between eruptions, waiting patiently to release the heat and pressure that builds slowly in chambers beneath the Earth's surface crust over years, decades, or centuries. Some volcanoes erupt with rhythmic regularity, allowing scientists to predict eruption windows with reasonable accuracy. Others remain dormant for extended periods, then awaken suddenly with little precursory warning of impending activity. The magma rises slowly through the crust, driven by buoyancy forces and pressure differentials between deep chambers and surface vents. This reminds us that volcanoes represent pathways for interior heat, to escape toward the surface. The molten material cools and solidifies after eruptions, then accumulates through repeated cycles. Even now, magma chambers continue to fill and pressurize beneath currently dormant volcanic peaks. Floods come with the rain, washing water across lowlands in patterns that have repeated for millions of years since water first fell from clouds and began flowing downslope toward the sea. Some floods are seasonal, occurring predictably when snowmelt or monsoon rains arrive to swell rivers and inundate floodplains. Others occur unexpectedly when unusual precipitation patterns or storm systems produce excessive runoff. The water carries sediment and debris downstream, modifying channel geometry and floodplain topography through each inundation event. This reminds us that water shapes landscape through hydraulic action and sediment transport. The floodwaters recede gradually as water drains back toward the ocean across weeks or months. Even now, rivers continue to flood their floodplains in cycles that persist through seasons and years. Tornadoes form and dissipate, spinning briefly before dissolving into the air from which they emerged, leaving trails of destruction in their passing through landscapes transformed by wind shear. Some tornadoes touch the ground for only seconds, creating brief but intense damage in narrow paths. Others maintain contact with the ground for extended periods, carving longer damage trails across regions. The rotating column of air extends from cloud base to ground level, creating the visible funnel shape observed from distance. This reminds us that tornadoes represent atmospheric phenomena too small and transient for reliable advance warning. The vortex contains the fastest winds found in nature's atmospheric circulation systems. Even now, meteorologists study tornado formation using radar and atmospheric data analysis techniques. Avalanches fall and rest, releasing energy in moments before coming to stillness on valley floors where snow accumulates once more across seasons following the destructive descent. Some avalanches move slowly enough to be outrun by experienced mountaineers and skiers traveling downslope. Others advance with such speed that escape becomes impossible for those caught in the path. The snow compacts and densifies as it moves, becoming increasingly difficult to move through or escape from. This reminds us that avalanches represent stored gravitational potential energy released suddenly by triggers. The snow settles at lower elevations where it remains until spring. Snowmelt returns water to natural drainage pathways. Even now, avalanche paths in mountains show obvious evidence of recurring slides through tree damage and exposed earth. Hail falls and melts, returning to water that flows back to the oceans from which it evaporated, completing cycles that repeat infinitely through seasons and years. Some hail accumulates in regions where temperature remains sufficiently low even after falling to the ground. Others melts immediately upon landing on warmer surfaces below the altitude where it formed. The ice crystals dissolve into liquid water that joins surface runoff and infiltrates into groundwater reservoirs. This reminds us that water cycles perpetually between atmosphere, surface, and subsurface reservoirs. The hail represents water in frozen form, temporarily removing it from the liquid phase before returning it. Even now, hail continues to form in thunderstorms when atmospheric conditions produce sufficient updrafts. Lightning flashes across the sky, illuminating clouds for brief moments before darkness returns and the atmosphere settles once more into stillness following the electrical discharge event. Some lightning occurs within clouds without reaching the ground, producing only sound and light visible from great distances. Others connect cloud to ground, creating brilliant illumination that burns after images into observers' vision temporarily. The electrical current flows through the most conductive path available, following air molecules ionized by the electrical field. This reminds us that electricity operates constantly in our atmosphere through charge, accumulation, and discharge. The energy released as light and heat persists for only milliseconds before dissipating. Even now, electrical activity continues in thunderstorms across the planet. Droughts persist and pass as water cycles through atmosphere and land, sometimes bringing scarcity and sometimes bringing abundance in seasonal patterns that repeat endlessly. Some droughts last for years, while others resolve quickly with returning rainfall. The land dries slowly, then recovers gradually as moisture returns. This reminds us that water flows between sky and earth in continuous cycles. Vegetation withers in drought, then grows again when water comes. The soil alternates between hard and soft with changing moisture conditions. Even now, droughts continue their seasonal cycles across the planet. Blizzards arrive and depart, depositing snow that falls gently or violently before the landscape transforms into white stillness once more following the winter storm passage. Some blizzards bring heavy snow, while others bring light accumulation. The snow covers everything, hiding the ground beneath white layers. This reminds us that winter brings snow to many regions each year. The cold preserves the snow until spring warmth arrives. Temperatures rise gradually, melting the snow into water that flows downward. Even now, blizzards continue to blanket landscapes in snow. Dust storms rise and settle, carrying particles that drift across vast distances before being deposited and becoming part of new soil across different regions of the world. Some dust storms are intense and rapid, while others spread slowly. The particles travel on wind currents across many miles. This reminds us that deserts produce dust continuously. Fine sediment moves from place to place through atmospheric transport. The dust settles eventually, enriching soil where it falls. Even now, dust storms continue their ancient patterns. Wildfires burn and cool, consuming vegetation in moments that took years to grow, leaving char and ash in places where green once flourished and thrived. Some fires are slow and cool, while others advance rapidly with intense heat. The wood burns away entirely or partially. This reminds us that fire consumes forests that take centuries to grow. The ash remains after burning, altering soil composition. Trees regrow eventually where fires once burned. Even now, wildfires continue to reshape forest landscapes. Earthquakes occur and cease, with seismic waves radiating outward through the crust in patterns of motion that gradually fade to silence, again following the fault rupture and stress release. Some earthquakes are strong, while others are weak and barely noticeable. The ground shakes briefly, then returns to stillness. This reminds us that earthquakes represent normal geological processes. Stress builds gradually until release becomes necessary. Waves carry energy across vast distances before dissipating. Even now, earthquakes continue daily across the planet. Volcanoes erupt and quiet, releasing pressure before settling into dormancy that may last for years or centuries until new pressure accumulates slowly deep beneath the surface again. Some volcanoes erupt frequently, while others remain dormant for extended periods. Magma rises and cools in cycles that repeat. This reminds us that heat persists within the Earth continuously. Pressure builds as magma accumulates in chambers below. Eventually, eruptions release the accumulated pressure and stress. Even now, volcanoes continue their ancient cycles of activity and dormancy. Floods rise and recede, following paths carved by water over countless previous inundations through the same valleys and lowlands that drain toward the sea. Some floods are rapid while others persist for extended periods. Water flows downslope, following gravity and terrain. This reminds us that water shapes landscape through repeated cycles. Sediment travels with the flowing water, altering channel geometry. Eventually, water returns to normal levels again. Even now, rivers continue their annual flooding cycles. Mountains stand and shift, moving imperceptibly across geological time, while appearing unchanging to human observers across their brief lifespans and generations of relative observation. Some mountains rise while others erode gradually. Rock layers fold and fault slowly over millions of years. This reminds us that mountains represent dynamic geological features. Uplift and erosion balance in ongoing processes of change. The landscape alters across geological time beyond human perception. Even now, mountains continue their slow transformation. Storms form and dissolve, appearing and disappearing across the atmosphere in seasonal cycles that repeat year after year, predictably according to climate patterns and atmospheric dynamics. Some storms are intense, while others are mild and brief. Air masses collide and create weather patterns. This reminds us that atmosphere undergoes constant change and motion. Weather systems form, develop, and decay in endless cycles. Moisture condenses and evaporates repeatedly in continuous circulation. Even now, storms continue to form across the planet daily. The ground shakes and stills, with earthquakes occurring regularly at intervals determined by tectonic processes operating far beneath conscious awareness and normal human perception of the world. Some earthquakes are frequent while others are rare in particular regions. Stress accumulates in crustal rocks gradually over time and then releases suddenly. This reminds us that earthquakes represent normal planetary processes occurring constantly. Energy stored in rock must eventually release through rupture. The cycles repeat endlessly as plates move and collide. Even now, earthquakes continue to occur across fault zones worldwide. Water flows downward, moving across landscapes in patterns governed by gravity and topography, reshaping terrain across vast expanses of time in cycles that began when water first fell upon the earth. Some water flows rapidly downhill in streams and rivers toward the sea. Other water seeps slowly into the ground, infiltrating deep into soil layers and aquifer formations below. The water follows the path of least resistance, carving channels through soft rock and soil over millions of years. This reminds us that water shapes landscape through patient erosion and transport processes. The sediment carried by flowing water deposits in layers across floodplains and deltas. Even now, water continues its ancient work of reshaping the planet. The sky darkens and clears, with storms arriving and departing in rhythms tied to atmospheric pressure and temperature differences that drive weather patterns across seasons and years. Some storms arrive quickly, while others develop gradually over days. Cloud formations build and disperse according to moisture and wind patterns aloft. This reminds us that weather undergoes constant change and transformation. The atmosphere moves energy from place to place through wind circulation and heat transport. Precipitation falls and evaporates repeatedly in endless cycles. Even now, the sky continues its perpetual cycle of darkening and clearing. Energy releases slowly or suddenly, depending on the accumulation rates and triggers that govern natural processes across different temporal scales and geographic regions. Some energy accumulates for years before releasing suddenly in catastrophic events. Other energy dissipates gradually through ongoing processes like erosion and weathering. The stored energy converts to kinetic energy in moving material or to thermal energy in heat release. This reminds us that energy flows through natural systems according to physical laws. The magnitude of release depends on how much energy has accumulated before rupture or transformation. Even now, energy continues to accumulate and release across the planet. Natural disasters continue to reshape the Earth's surface, following patterns established long ago and continuing into an indefinite future, with rhythms operating beyond human control or influence. Some disasters reshape landscapes visibly, while others operate so slowly that change is imperceptible across human lifespans. Yet the cumulative effect across millions of years transforms continents and ocean basins entirely. This reminds us that natural processes operate on timescales vastly different from human experience. The patterns repeat because the same physical laws govern processes perpetually. The cycles continue regardless of human wishes or desires for stability. Even now, disasters continue their ancient work of transformation. Time passes gently and steadily, with natural processes unfolding across the planet in rhythms that repeat continuously, without ending or changing fundamentally in their essential character and nature. Some processes move quickly, while others progress almost imperceptibly across years. Yet all processes operate according to immutable physical laws and principles. This reminds us that time flows onward regardless of human perception or awareness. The planet evolves through processes that operate ceaselessly regardless of human activity or observation. Change occurs constantly even when humans cannot directly perceive it happening. Even now, time continues to pass as natural processes unfold. The cycles continue their ancient patterns, operating according to fundamental laws of physics and chemistry that govern all matter and energy throughout the universe. Some cycles are rapid, while others require millions of years to complete. The patterns repeat identically across different locations and time periods. This reminds us that nature follows consistent principles everywhere and always. The same forces that shape mountains also shape riverbeds and coastlines. Universal laws apply equally to all parts of our planet. Even now, cycles continue their timeless patterns. Seasons change and alter the character of landscapes through temperature and precipitation variations that follow regular patterns established by Earth's orbital mechanics. Some seasons bring warmth and growth, while others bring cold and dormancy. The transitions occur gradually over weeks as conditions shift. This reminds us that seasonal patterns structure much of life on Earth. The cycles repeat annually with remarkable regularity and predictability. Change marks the passage of time through observable seasonal transitions. Even now, seasons continue their eternal cycle of transformation. Night falls and light returns as Earth rotates to bring darkness and illumination alternately to different parts of the planet in daily cycles that have persisted since the planet's formation. Some places experience extreme day-length variations, while others have relatively constant day and night lengths. Yet all locations experience the basic rhythm of darkness and light returning. This reminds us that celestial mechanics govern the basic rhythm of day and night. The rotation creates the diurnal cycle that structures daily life and biological rhythms. The pattern repeats identically each day with mechanical precision. Even now, night and day continue their eternal cycle. The world turns slowly through space, orbiting the distant sun at a distance that permits liquid water and life to exist in the remarkable conditions found on Earth's surface. Some parts of the planet are closer to the sun, while others are farther away due to Earth's orbital characteristics. Yet all parts maintain habitable conditions through planetary dynamics and atmospheric circulation. This reminds us that Earth occupies a special place in the solar system. The balance between planetary distance and atmospheric properties permits life to flourish. The orbit remains stable across billions of years due to celestial mechanics. Even now, Earth continues its orbit through space. Existence persists through periods without end, with patterns that echo and repeat across time in ways that structure the universe and guide all phenomena within it toward ongoing cycles of change and transformation. Some patterns are simple, while others are extraordinarily complex in their structure and behavior. Yet fundamental patterns underlie all phenomena observable through science. This reminds us that creation operates according to lawful principles. The universe follows mathematical laws that govern all processes without exception. Patterns repeat at different scales, from atoms to galaxies. Even now, patterns continue to structure all existence. The universe continues its slow unfolding, with time advancing steadily forward through eons and ages toward a distant and unknowable future where patterns established long ago will continue to shape events and processes eternally. Some processes move toward increasing entropy, while others create temporary order and structure. Yet all processes operate within time's forward-flowing arrow. This reminds us that the future remains open and undetermined, while the past remains fixed and known. Time flows onward, carrying all things toward their eventual fates and conclusions. Patterns established now will influence events across ages to come. Even now, rest comes gently as natural processes continue their eternal work.